Now, okay, so let us start the second part of this lesson. Now we are ready, hopefully, for the definition of a definite integral. So can you motivate it for me? So if you want to define, I want to see what you learned. So if I want to define an integral, a definite integral, what ingredients I need? I need a function. Yes. What else I need? I need a closed interval. Yes. And I need some property for f. Do you remember what was that?
Bounded.
Bounded. So f should be bounded on A and B. Not everywhere, but if I limit myself to A and B, f becomes bounded. Yes. And then one more thing. So these are a function, an interval, f is bounded. Now I want to tell you what do I mean when I say f is integrable. Integrable on A and B. I have written everything extensively in the lecture notes, but that is why I don't write very precisely. So I want to know what do I mean by when I say f is integrable on this closed interval A and B. Can you define it for me? Motivated by the idea of the area. If there exists a unique number I such that, okay, can you complete it for me? What was the property of that area? Area was less than every upper sum and it was larger than every lower sum. So if there exists a unique number I such that U, L, F and P is less than or equal to I and it is less than or equal to U, F and P, yes, then F is said to be integrable. On A and B, on the interval A and B. And I is called the definite integral of f on or over, it doesn't matter, A and B. Okay? And we denote it by this symbol, integral from A to B, f. Yes? I hope that you see that it is very impractical definition. Yes?
It's only for bounded. If it was not exactly
bounded, that will be the topic of the improper integrals.
Okay.
Yes, but for the time being, everything is bound. The function is bound. So I hope that you see that this is a very annoying definition. So because how many partitions you can imagine for your interval A and B? You can imagine infinitely many, but even among those infinitely many, we have regular ones and then we have irregular ones. Regular ones have some pattern to them, so might be studying them is easy, but this is not claiming only for pattern for the regular one. It is claiming that if there is one unique number which lies between all these numbers, that number is called the definite integral of your function. And then we say that the function is integrable. Just I want to give you a feeling that sometimes, very, very seldom, that this definition is helpful. Okay, to even calculate the value. Okay, so for example, the simplest possible example is the function, the constant function. It is good because it will allow you to digest what I told you before. So let me consider a constant function, c is any number that you like, but fix it, and I give you any interval that you like, A and B. You hopefully agree that f is bounded because it's a constant function, okay? But let us say that if this function is integrable or not. How do you do that? You would ask, okay, let me pick up a partition. Yes, let us let P be equal to x naught up to xn be a partition. Okay? Any partition, not regular. Any partition might be regular, might be irregular, but it's a partition. Do you think I can calculate the lower sum for this very simple function? The answer is yes. Write the formula of the lower sum first. Do you remember? It is sigma. K goes from 1 to the number of nodes. Little m sub k, which means infimum or minimum in this case because the function is continuous, multiplied by delta xk. One more question, I just want to test your understanding. Can I replace delta xk here to b minus a over n? No, why not?
Because we didn't know if it's regular.
Yes, if it is regular I can do that, but if it is not regular I have to keep it. But it doesn't matter here, you know why? Can you tell something about the minimum of m, the minimum of the function on the kth interval? But the function is horizontal because it is a constant. So it doesn't matter. If I ask you, can you tell me what is this minimum? What do you say?
C.
It is C. Do you agree? So this means that I can write it as C, and then I would write k from 1 to n, and then I would write delta xk. But C is a constant. I can pull it out from the sigma, and then it becomes sigma delta xk, and k goes from 1 to n. But I know something about this. What is this one? This is adding all these lengths of subintervals. Regular or irregular, I don't care. What I am doing, I am adding all these lengths together. What I get at the end? What do I get at the end? I have a partition, I have just chop it up, and I am adding these lengths together. So what happens?
It's just a length.
The length of the total interval. What was the length of the total interval? B minus A. So this number is B minus A. And the answer will be CB minus A. Do you agree? Mm-hmm. So, regardless of what partition I choose, every lower sum is C times B minus A. Do you agree that if I write the same scenario for upper sum, what do you think will happen? For the upper sum, it becomes sigma. The only difference is that this becomes capital M multiplied by delta xk. What is capital MK in this case? Remember, the line is horizontal. It's just the same C. The maximum and minimum are the same. So this is again C for every k. So I pull C out, and then I am left with the same calculation. And then if I ask you what is this, this is the sum of the lengths, so it becomes B minus A, so it is CB minus A. So what does it mean? It means regardless of the partition that I choose, the lower sum is CB minus A, this is the lower sum, and the upper sum is the same. Yes? Is there any one unique number sandwiched between these two numbers? Yes, there is one. I am looking for a number I, which is on the one hand smaller than all upper limits, upper sums, and simultaneously greater than or equal to all lower sums, which are accidentally the same. Yes? How many numbers lie there? One. And what is that number? The same number itself. Is that clear? So this means that for this very simple function, I was able to use the crude definition to show that the function is integrable. I was also able to find its value. So if I want to write something here for you, so f is integrable, what do you say about this symbol? What should I write in front of it? This is the unique number with that property, but I realized what was the unique number? It was CB minus A. So we calculated this one as well. Yes? Because regardless of which partition I choose, the lower sum is this number and the upper sum is the same number. So yes, there exists, because we know that C times B minus A definitely satisfies this condition, so it is between them. And it is the only one between them. So according to this definition, very crude definition, it is integrable, and that is the value of the integral. Is that right? But I hope you see that it is extremely hard for very wild cases, yes? One more thing I want you to see, because that's also good. There is a very famous function in mathematics called Dirichlet function. It's a German mathematician. Dirichlet function is defined in a very nice way. That's an artifact for these kind of things. Mathematicians like these things, okay? So let me show you why Dirichlet. Dirichlet function is defined to be having two outputs, either 1 or 0. 1 if the input you give is a rational number. 0 if the number you give is not a rational number. It's an irrational number. For example, if I ask you what is d acting on 1 over 2, what's the answer? 1 over 2 is rational, and the output will be 1. If I tell you what is d of pi, what's the answer? Pi is irrational, so d of pi is 0. So if I ask you what is d, d is just 0 or 1, jumping up and down, but jumping extremely fast, because between two rational numbers, how many irrational numbers are there? Between any two real numbers, I have infinitely many rational numbers, and I also have infinitely many irrational numbers. So the function is probably very simple, it is 0 or 1, but this jumping up and down is extremely fast. You cannot take it, but you can imagine, but we cannot draw any picture. Now the question is that, is this function integrable? This is a very famous example that the answer is no. But understanding it is actually very important because it's very simple and it will help you to understand the definition of the integrability. So let us try to see if this is integrable or not. First of all, is Dirichlet function bounded? Yes, because either it is 0 or 1, so it is bounded, okay? But it is not continuous because it's jumping up and down, yes? It is bounded but not continuous. Okay, but now let us pick a partition, any partition that you like. For which number? So I want to show that, for example, let me pick a very simple interval, 0 and 1. I want to show that d on that interval is not integrable. That is my intention. Let us do that. Pick up a partition for your interval, 0, x1, up to xn, any partition of 0 and 1. Okay? Not necessarily regular, any partition. And n is also arbitrary. You can choose n as any number you like. Okay, but now can you help me to find L of Dirichlet function and this partition, whatever the partition is? The first thing you do, you write a formula. So you write sigma little mk delta xk, k goes from 1 to n. Delta xk, I cannot say anything about that because it is not guaranteed, this is regular, so I have to live with it. I cannot change anything. But can I say something about m sub k? M sub k is the minimum of the Dirichlet function on the kth interval. But the Dirichlet function gets 1 and 0. Is it guaranteed that Dirichlet function gets 0 everywhere?
0 everywhere.
No, it gets, I mean, in any interval, is it guaranteed that I have 0 for Dirichlet? Because
yes.
in any interval, it is guaranteed that there is irrational number. So in that case, this little mk for all sub-intervals is what? Is 0. And then of course it means that all the terms are 0, so when I add them up, the answer also becomes 0. So for the Dirichlet function, no matter which partition I choose, the lower sum is always identical to 0. But let me also calculate the upper sum for the same partition. The formula goes from 1 to n, capital M sub k, delta xk. Help me, what is capital Mk here? Is the maximum of the Dirichlet function in the kth interval. Because in the kth interval, there is guaranteed to be rational numbers, so the maximum will be 1. So this capital M is 1 on each one of them. So it becomes sigma, this one is 1, and then I am left with this. But can you tell me, is there something in particular I can say about this sum?
It's just the length of
It's just the length of the total interval. Yes, because it is the sum of all these lengths. It becomes 1. Is that right? So the lower sum is always 0 and the upper sum is always 1. So this means that the lower sum, all the lower sums are here and all the upper sums are here. Yes? How many numbers are sandwiched between 0 and 1? Infinitely many. But I need a unique one. So this is not integral. Is that clear? So this definition is more or less useless all the time, except for these very artificial functions and simple functions. Okay? So really it is very clear that the notion of integrability needs something more. Okay? So that's why there are a lot of theorems that guarantees integrability. For example, one of the theorems is continuity, but that is hard to prove. It's beyond this course. So if a function is continuous, it is guaranteed to be integrable. Okay, so, and for example, another one is that if a function is a monotone function, bounded monotone function, it is also guaranteed to be integrable. So because the idea of integrability is not that easy to understand, or I mean to work with, so this is why there are very nice theorems made by mathematicians for case-by-case studies. At least you understand what is going on, yes? Okay, so now let me see what else we have. Okay, so it's very hard for me to write all these formulas because it's just a waste of time. But let me talk a little bit about one more thing which is important for this course. Usually the hard questions are coming from this topic. And that is the notion of Riemann sum itself. Okay, not the lower sum or upper sum. We have also the notion of... sorry. I forgot to say something. Okay, so there is one theorem that I want to add, and the proof is also hard. I want to skip the proof, but there is a very nice theorem called Archimedes-Riemann theorem. Okay, this tells you that if you calculate upper sums for regular partitions only, yes, and lower sums for regular partitions, and then you are lucky, and when you calculate the limit of these two, when n goes to infinity, they turn out to be the same number. It is guaranteed that your function is integrable, and the value of this limit is the integral. Okay, so it means that if the limit of this is equal to the limit of L, and it becomes I, regular, yes, then f is integrable on a and b, and the integral of the function from a to b is exactly this number. Okay? Is that understandable? So this is the most efficient theorem after definition. So you need to sit down and really prove it. It is not in this course. It is a mathematical analysis theorem. But this is why regular partitions are so important. Because even though the definition needs all partitions, but because of this theorem, working with regular partitions are usually simpler, and it is advantageous because of this theorem. And do you remember I solved one problem in the exam, so I don't want to redo it again. Do you remember what was that problem? We had this function y equals to 3x, yes, and it was, if I remember it correctly, from 2 to 3, yes, Do you remember in that exam problem, they told us to calculate L of the function with regular partition P of n? Do you remember? I don't remember what was the, can you have the notes here?
Yes.
So can I see what was the answer? This one. So if you go, oops, thank you. What, this number, 6 plus what? Can you read it? 3 over 2?
N minus 1 over n.
N minus n. Okay? So do you remember, for that function and this interval, that was exam problem, I calculated this for this regular partition. Yes? And then do you remember, next time we take the limit. So when we take the limit of L, F and Pn, what did we get? We get 15 over 2. Okay? But it is not guaranteed that my function is still integrable. I have to do similar calculations, and I want you to do it at home for you. And then take the limit. If you are lucky, in this case you will, and you get 15 over 2, and they are the same, then you will say that because of this Archimedes and Riemann theorem, the function is integrable, and this common value is the value of the integral. Is that right? So it makes it a little bit simpler. The definition is very hard, you know, if you want to work with all possible partitions, it's extremely hard but if you want to work with regular partitions, because they are regular, you can do some calculations. And that is enough, according to mathematicians that have proven this theorem, that is enough for us. Is that right? But still, I hope that you agree with me, it was not possible if I changed the function to this one. Do you remember? It was useless again. So even if this is good, it was working, it was better than the definition, but still it is not very powerful. Is that clear? Okay. Now let me go to the Riemann sum. So what is a Riemann sum? A Riemann sum is denoted by R, upper sum, lower sum, Riemann sum. Okay? The Riemann sum has 3 ingredients. The function, the partition, and a vector, which I call it a tag. So what is this tag? If this is my partition, x0, x1, up to xn, if this is my partition, a tag of a partition means choose n points from n subintervals, any points you like. For example, let me consider this one. Do you remember my function was something like this? I have erased that, but this is the function y equals to x squared. Do you remember? I started from 1 and then we went to 5. Okay? So what was the first partition? It was not even regular, so the 2 and then 3 and then we jumped to 5. So that's my partition. So this partition that I have in this case is just 1, 2, 3 and 5, and my interval is what? My interval is from 1 to 5. So we already learned about how to write U and L for this partition, for example. But what is the meaning of a Riemann sum? A Riemann sum means that you have to choose something else. What is that something else? From within, not within, from every interval, you pick one random or any number that you like. For example, in this interval, you can choose 1, you can choose 2, or you can choose any number in between. So for example, let me call C1 to be, 1.5. This is called a component of my tag. Okay, choose another number within the next interval. When I say next interval, you can choose 2 if you like, you can choose 3 if you like, and you can choose any number you like. So let us say, what is your preference? For example, let us choose C2 to be 3. I am just jumping here. And let me choose one more tag. Between 3 and 5, you can choose 3 if you like, you can choose 5 if you like, or you can choose any number in between. So for example, let me choose 4.25. Yes? So then this vector has 3 components. The first component is 1.5, the next component is 3, and the next component is 4.25. Okay, but what is the Riemann sum? The Riemann sum is very simple, even simpler probably that. The Riemann sum that you see here is a sigma. So let me write it like this. I will choose f I pick the first component and put it here, and then I multiply it by delta x1. So the difference is that in the upper sum you have capital M. In the lower sum you have little m, but in the Riemann sum you have f of C1. Yes, and then you do the same thing for the next integral. So what is that? F of the second component multiplied by delta x2, and then the next one is f of 4.25 multiplied by delta x3. So that is the Riemann sum for this tag. If I keep f the same, if I keep p the same, but if I change my tag, meaning that if I start changing these numbers, I will probably get a different number. So the lower sum and upper sum are only sensitive on function and the partition. But the Riemann sum is sensitive to three ingredients: the function, the partition, and the tag you choose for that partition. If you keep f and p the same, but you decide to change the tags, the numbers will be different. But let me ask you, do you see that the upper sum and the lower sum are special cases of Riemann sum? Yes? Do you agree? Because in the upper sum, in the case that the function is continuous, of course, in the case that instead of choosing any number, I am looking for a tag which gives me the maximum for upper sum, minimum for lower sum. Is that right?
Yeah.
So, if I want to say something about R for a fixed F, for a fixed P, and I want to write L, and I want to write U, can you feel there is a relation between L, R, U, if F and P are fixed, and then you are allowed to change tags? What do you think will be the relation between these three numbers?
It's in the middle or equal.
Yes, so it means that lower sum
Yeah.
is less than a Riemann sum. This is also less than an upper sum. Is that right? So now look, if the function is integrable, this relation holds for also regular partitions because it holds for any partitions. But now, if the function is integrable and I myself intentionally choose regular partitions, then the limit of the left-hand side is the number to the integral. The limit of the right-hand side will also be the integral. So then what happens for the limit of the middle one? Will be the same by squeeze theorem. So this, what does it mean? It means that if it is guaranteed that your function is integrable, the limit of any Riemann sum, not just the upper sum and the lower sum, for any choice of tags will converge to the same value. Okay? Is that clear? Okay, so it is very important. Lower sums and upper sums we learned before. We now introduce a new concept which is called the Riemann sum. It has one more ingredient to it, so you have infinitely more degrees of freedom. So you fix F, you fix P, okay? L and U will be fixed, but still you have infinitely many degrees of freedom for R because you can play around with these tags. But it doesn't matter if the function is integrable. This limit goes to the I value, integral value. This will go to I value if I choose regular partitions. So it means that if I choose regular partitions, the limit of R will also be the same by squeeze theorem. Yes? Is that understandable? Mm-hmm. Okay, but this is very important for this course because the hard questions they usually ask from here. For example, if you want to calculate this limit, k over n, n goes to infinity, k goes from 1 to n. That's a complicated limit. F is a function which is bounded, for example, let us say interval is between 0 and 1. So this is the question we want to address. We want to understand how to calculate these limits. If f is a function which is integrable on the 0 and 1. The whole point is to do the reverse engineering. Yes, it is a little bit strange logic because in principle we use these kinds of limits to calculate integrals as we did here. I found this, I calculate the limit, and then I say this limit is the integral. But now we want to change the logic. Okay? A limit is given. If you can interpret this limit as an integral, and if you know how to calculate that integral, you can use integrals to calculate limits. Okay, so you see, the logic is not this way. The logic is that if you manage to find L and take limit, if you can calculate the limit, that limit is your integral. But it doesn't hurt if I do it the other way around. If I want to calculate a limit and I can convince myself that limit is equal to a given integral, and if I can calculate that limit, it means that I was able to calculate the limit. If I can calculate this integral, it means that I could calculate the limit. I want you to understand the logic. Okay, but let me ask you one question. Can you engineer this as a Riemann sum? For example, let me tell you that f is integrable on 0 and 1. I guarantee you that the function in this sum is integrable on 0 and 1. But now can you tell me, can you see that this is a Riemann sum? Let us see that. So, if I go from here to here, this is 0, I want to exaggerate a little bit, this is 0 and 1. So let us chop the interval from 0 to 1 to n equal pieces. N equal pieces, okay? So what, for example, let us concentrate on, let me put some dots here, and let us say that this is x sub k minus 1, and here is x sub k. This is the kth interval after my partition into regular partitions. So what is the length here? Can you tell me what is this length? The whole interval is of unit length. I am chopping it into n equal pieces, so each piece is 1 over n. Okay. Now, can you tell me what is... Okay, so now what I want to do, I want to find a tag for this partition. So let me design this for you. So what I want to do, I want to tell you what to choose for the kth position. Yes? If I want to write a Riemann sum, I need to choose a tag, because you know that I fixed a function for you, I fixed the interval for you, I fixed a partition for you, but still I have a lot of freedom in choosing my tags. Okay? A tag has n components. Why? Because we have n pieces and I want to choose 1 point from each component. And I am free to do whatever I like. Okay? But I want to do it in a way that it will allow me to calculate this particular limit given in the problem. Okay? So let us concentrate on the kth position. I am telling you that you are allowed to choose any point as your tag for this interval. But I am demanding you choose the last point. Okay, so what I want you to put here, I want you to put ck to be equal to xk. For ck, you can choose this one, you can choose all these points, you can also choose this one. But listen to me and choose the last one to see what happens. Okay? Now, do you understand what's going on? Okay, can you tell me a formula for x sub k? It is not on the board, but hopefully you remember. I start from the first one, and then I will multiply k by 1 over n, because each one of these pieces is this one. So what happens? It becomes k over n. Yes? And I am asking you to choose the kth position tag to be xk. Okay? And then I want you to write the Riemann sum for my function, for that partition, and for this tag. So can you write this Riemann sum? the Riemann sum has a delta x in it. So it becomes sigma, k goes from 1 to n, and then I have delta xk. And then I have f at that calculated at that chosen tag. So in this case, it will be f of ck. This is the formula for Riemann sum. This is the general formula for Riemann sum. But now let us go forward. What can I write for delta xk? Is the length of interval number k, but all of them are 1 over n. So this becomes 1 over n. And then what I can write for fck? I ask you to choose ck to be xk, and xk is k over n. So it becomes nothing except f of k over n. K goes from 1 to n. Yes? So let me just review everything quickly. I want to calculate this limit. I am doing some kind of engineering to show that this is a Riemann sum if I engineer it appropriately. So it was not that easy to guess how should I choose the tag, but everything else comes automatically. So I am telling you that concentrate on the kth interval of length 1 over n, and I ask you, you are allowed to choose any tag you like, but for this problem I ask you to choose ck to be xk. And then calculate the Riemann sum. If you start calculating the Riemann sum, what do you see here? You see exactly this expression. Okay? And you might say, how can I understand that? I will tell you how to do it a little bit, might be tomorrow. But here, at least I was able to show you that if you do this, this sum will be your Riemann sum. Okay? Now, I am claiming that f is integrable. So if f is integrable, the limit of every Riemann sum, no matter what Riemann sum I am looking at, will be the value of the integral. So this means that if I want to solve this problem by using the integral, so what happens? That question mark, which is my limit, it becomes equal to the limit of the Riemann sum. Yes? Because I was able to convince you, hopefully, that this expression that appears in front of that limit is nothing except a Riemann sum of an integrable function. So this means that this limit becomes equal to the integral of my function on my interval. Yes? So what happens? It means that I was able to reduce my problem of calculating a limit to an integral. I am not telling you that I was able to calculate my limit, but I'm telling you that I was able, hopefully, to convince you, that was my intention at least, to convince you that this limit, if f is integrable, is exactly equal to the integral of my function from 0 to 1. In the future, next lesson, if I know how to calculate this integral, it means I was able to calculate this complicated limit. Is that clear? For example, I don't think that these limits are simple. For example, let me choose the function f of x to be equal to sine x. For example. Okay? Let me rewrite this for this function. What will be the limit? It will be the limit of sigma k goes from 1 to n, 1 over n, f, which is sine of k over n. It becomes sine k over n. And let me open it up for you to see that you are doing really something. Let me open up the sigma. So I copy and paste the limit symbol. If I put 1, it becomes 1 over 1 sine of 1 over n plus, and then if I choose, this is 1 over n. Because this is n, I have to change k. I choose k equals to 1, the next one will be 1 over n sine 2 over n, and the next one will be 1 over n sine 3 over n, and this list will continue until the last one, n 1 over n sine n over n. Okay? And if you don't mind, let me factor 1 over n out. So this is why it is important. We will talk about this extensively later. So might be in the exam you get this limit. I want you to feel, if they ask you to calculate this limit, this is not easy at all. Yes? So if I want to calculate this limit. But I was able to show that whatever it is the integral from 0 to 1 of that function, sine x dx. This is among the simplest integrals that we will be able to calculate. So finding this limit becomes so simple as calculating this integral in the future. But you have to be able to reverse engineer and interpret these kinds of limits as limits of some particular appropriate Riemann sums. And then they said, okay, because my function is integrable, instead of calculating this limit, I will calculate the integral. Hopefully that integral is manageable, and we can do that. If we can, then it means that we can calculate this limit as well. Is that clear? Okay. So, of course, of course there are some problems. I will start doing it tomorrow. This is the most important part that I have seen. A lot of questions coming from calculating limits using the idea of integral. Because somehow you have to understand all these things to be able to do that. So, any questions? If you didn't understand that one, because it was the very last part, you are a little bit tired, I will repeat this tomorrow. And I will, of course, tomorrow complete the integration by parts, and then method of partial fractions, and work a little bit on this. And then there will be one more lesson left on Friday. Any questions? Yes, please.
Is it possible to add tomorrow's slot to the calendar? Because I don't think it. I checked and I couldn't find it there.
No, it is probably changed. So I have to contact the people, because do you know if E31 has a camera in it? Because if there is no camera, I can check it myself. I will send a message to you. But please check the announcement. I don't know how to add it to the schedule.
Okay, that's fair enough.
I will actually send a message.
If it's not as easy, then fair enough. I thought it was a simple click.
No, it is the simple click, but because I don't know how to do it.
Enough. Yeah,
Yes, but I will send a message to you. Yeah, okay. Yes, because the old one that I sent, they have changed the room. It was D37, but it is now